Okay, good morning, everybody. We don't have that much longer with each other, at least in this plane of existence we call 110. Um, Today we're going to talk about looking at a system from a transient perspective, right? But as you can make up your own assignments in LTspice, there are some pitfalls when you use a behavioral source. So I just thought to show you what goes on. All right. So, what we have here is a circuit, an RC circuit, and we have a behavioral source that we just say the voltage input is on node 1, and we give the Laplace, and that curly bracket is how we tell things are a variable, 2 pi fc. And so, when you parameterize things like this, you can rapidly design things back and forth. And then the way well, actually, I don't have it, but sometimes I even have the cutoff frequency in the simulation, and then you have the lower range and the upper range, and it'll always show up with the corner frequency in the middle. Um, when you're doing documentation at work, right, you can just, like, why do it this way? It seems like it's a lot to set up. But if you get it all working and saying the cutoff frequency in this case is 1 hertz. Then they come back and say, oh, you got to redo everything. The spec changed. The customer wants 2 hertz. Well, you just change 2, right? And then everything else will calculate out. Not only that, with the documentation, but even if you were making a data sheet, you can use Python to write Word documentations based on algorithmic things like the filter response is this. Um, takes a bit of doing. And by the time you're done, you would have maybe just wished you did it by hand. But so this is great though. The Bode plot works great. Now, the thing is though, is you can actually turn this into a transient simulation by just transient, right? You have a step and all of that. And you can see that V2 and VH are, at least from a plotting standpoint, indistinguishable, right? Now, if you zoom in, you might see where it doesn't overlap perfectly. But what's great about this is that you can set up the Bode plot and the Laplace and then easily see what you're going to get in the time domain, right? It's actually faster that way. You actually design the filter in the frequency domain. Well, what about second order filters, right? And in this case, I've got an RLC, which I can program the same way. And then we got low pass, Laplace, band pass, notch, and high pass, where the Bode plot, the transfer functions are all there, right? And then over here, you can see that like low pass is node 3, high pass is node 2 to 3, right? So I can do all of this, right, with one circuit. So there's our low pass filter with various damping coefficients. And you can see that the lower the damping coefficient, the higher the peak, if you will. This isn't a peak, but it's certainly higher than a second order system. Okay. High pass, same deal. You can see the band passes all working very nicely. Oh, and yeah, the high pass and the behavioral are all the same. You can't tell the difference, right? Same with the notch. Now we look at the low pass step response, and you can see a lot of ringing. Like ringing is oscillation, which means imaginary numbers, because you're storing energy without dissipating it. So the damping coefficient is going to be small. When you put the denominator into the quadratic equation, you're going to get complex poles, right? But you can even see, so it's what? We have 0.1, 0.707, 1, and 10. So 0.1, it's oscillating quite a bit. So it's certainly underdamped. Then 1 has a smidgen of overshoot and then settles. And that's kind of how you can tell the Butterworth is that it rises and doesn't oscillate back. Then critically damped is right below it. The thing is if I had 0.9 or 1.1 coefficient, it'd be very hard to just tell without context what is what, right? So I originally envisioned, here's a filter, here's a transient response. Tell me what it is and tell me the doping coefficient. Woo. Little Maddie 153 jumped in there. The damping coefficient, right? The thing is you can't really do it because critically damped and a little bit underdamped and a little bit overdamped all look the same, right? And if I wanted something to be like this one here is clearly the overdamped response, but with a different omega naught, I could make that the critically damped one. So then upon researching things, there's a lot of algorithms to find all the components of a underdamped system. But when you look at critically damped and overdamped, nobody cares. Now, I have these notes, I think I hid them because they were way too complicated to figure out how to do it. And you needed a computer to backfit everything. But what I suspect is that underdamped systems are the more used, the more useful, that it's a trade-off between the settling time and how fast the rise time, that nobody even bothers with critically and overdamped, okay? All those elliptical filters all have complex poles, right? So just nobody felt it was worth it. High pass, obviously the one oscillating a lot is the underdamped one. But then notice we've got several crossing, right? So the heavily oscillating one is 0.1. Then we have 0.707. And then we have even 1 crosses and comes back. And that's just the nature of the high pass. So you can't really tell, if I just gave you this plot without anything else, the difference between these two, which one's underdamped, which one's overdamped. And the overdamped one it's a little hard to see, but it should just come down and not oscillate at all. All right. But here's the thing, it's working, but notice right in this regime, and this is a part of these slides, is that you're starting to see the green and the blue deviate. So you have the high pass filter done with the RLC circuit with ideal components and the Laplace, and it's starting to deviate. And now here's the band pass. And it completely falls apart. All right, it doesn't work. And Notch has its issues. Some work, right? you can see there's like little, so it's working. Here you might go, what's this line out of here? Well, the other ones are probably working because it's overlapping. So it's just, so let's see, where are we going? So upon investigation, when you run through their documentation, the idea of taking a Laplace transform and making a transient of it in this way, right? Rather, I mean, if you just took the inverse of that Laplace, you would get a plot, and that's what SIMPy will do, right? Or LCAPI, if you give it a transfer function and say plot the step response, it takes the inverse Laplace transform and plots that. So it's perfect in that sense. But doing it in this form is an area of ongoing research, which means, you know, it's working well enough for now. And then what they'll say, if you really, then somewhere else, or maybe even in the same help file, you make a second order system out of RLC circuits. And it doesn't have to be physical, right? You can have large inductors, large capacitors to do any second order system like a pendulum or things like that. You just got to make sure that on the inductor, you set the series resistance to 0. That can throw things off a little bit, like it comes with a series resistance. So regardless of whether it's an airplane wing or a train or whatever, if you want both, you use an RLC circuit, and you can program it the same way, right, to get the response you want. Okay, so that's, but if you see me, usually I'm showing you the low pass, and I'm showing, oh, check and non-check. That's because it's that one works like kind of no matter what. All right. Also, oh, well, yeah, it was so important I wrote it down in the slide. The other thing is that we have, if we go back to our control theory, right, in the first equation, we have a pole on the right-hand side, so we're going to get exponential growth. So it has a hard time simulating that in the time domain. And then here, this should be an oscillator, and it doesn't always oscillate. Right, so that's the, so I don't even have any slides. So if you want, you design your filter using any kind of filter you want. You create a behavioral voltage source and check the Bode plot. If you're using low or high pass, the transient will work right away. The notch and bands, use an RLC to check the time domain. And then you implement with op amps. Because the op amps, no matter, there is no ideal op amp in LTspice, right? There's gain bandwidth, finite gain. And so what you see at the high frequencies is that there's a deviation. And then for like an unstable system, I think what I'm saying there is you can use a negative resistance and it'll oscillate, right? But you need that kind of analog circuit. So that's really to help you with the next bit. But any questions on the LTspice part of it? That's the thing. LTspice is used by a lot of companies, even analog devices competitors, right? You know, we often talk about Silicon Valley, you know, doing the work in your garage, right? Well, you don't need to be in the garage. You can use LTspice at the kitchen table. You know, it's just fine. Right? Or, and with the layout, you can send a PCB to Bay Area Circuits and have it come back, pretty cheaply. Etching and making your own boards is a real pain, let's just say. But it can be fun to do. So if you look at things that you've had in or will have, like we have a class on field programmable gate arrays. So the same one you use is used by any university, by real industry companies, and you can have that development board and you can do your research or product development, in the comfort of your own home or Phil's or the coffee establishment of your choice. All right. So now let's just start talking about simple things from a transient. Okay. So we have this Desmos can be pretty quick, but it also has, some limitations. So integrator, 1 over S, or differentiators, right? So if red is the step, right? Well, from convolution or integrating a constant gives you a ramp, straight out of Calc 1, right? Then, and the differentiator S takes the difference of anything. So we have a square wave, and you can see I'm taking the derivative. No, that's not right. I have a square wave, and I'm integrating up, and then it goes negative, and I'm integrating down. All right. It's not really, the differentiator is not really coming out. Because if I differentiate a step function, I get a delta function, right? So if I differentiate this triangle, right, I should get a positive slope and a negative slope. Differentiators are noisy, so they're not used much. So if you take a differential equation and you want to turn it into an op-amp circuit, you convert it to integral equations because it'll be a lot less noisy. If you go over to room 387, there's a poster of the butterfly effect that used to be done in 122. You make that out of op-amps. All right, so first order, high and low pass, right? So purple is high, we're detecting the edge, right? Red is step. We're rounding the edge and passing DC. And you should just know, right, that the bigger the tau, the longer it takes to settle. So this is taking longer to settle than this over here, all right? And really, that is like, I think, the 5th question on midterm 1, right? It's not really okay. Now, here, we have the high pass, low pass, and we have a damping coefficient of 10, 1, and 0.1. And you can see, this gain here at omega naught is very high. That should be at -6, and then this will be below that. Now, when you go and actually take the inverse Laplace transform of the step function, you get this equation. So you get 2 decaying exponentials for overdamped. Overdamped because there's 2 separate real roots. The poles are these numbers here. It gets really involved, which is why you've not seen a homework where take the inverse Laplace transform and tell me the equation and plot it, because really you just identify it. Then the critically damped, we have 1 decaying exponential and then a decaying exponential times time, and you can see those plotted out. The high pass, right? All the equations are there. The underdamped takes a bit of doing. Okay. The band, what I realized is I could subtract from the input the low and the high, and rather than come up with a whole other equation, I just did it the easy way. And then for the notch, right, it's the high and the low added together. Now we have a tale of woe, which means I got bit. And since I got bit, I want to prevent you from getting bitten. And so I want to teach you about it. But what it happened is that I got bit doing something that I thought was simple and according to theory, and then it deviated quite a bit, but it was theory that fixed it. So many times I'll read, oh, I can't wait to leave this place and stop learning theory and get out in the real world and doing stuff for real. And the thing is while theory is real, it's just usually simplified reality. And if you make things too complicated, it can be hard to model and understand a system. And so just like with the gain bandwidth, that's more reality. But what do we end up doing as designers? We stay below the gain bandwidth limit, and then the simple equations work, right? So what we have here is before the invention of the ADLM 2000 is a Bode plot of an RLC circuit, and I use Python to control the function generator and oscilloscopes and all that. So you can see that the magnitude is pretty smooth and looks pretty reasonable, and that the phase is jumping around a bit, and I can't even get out to minus 180. And even still, non-ideal RLs and Cs, that phase might come back up. All right. So what do? I find omega naught by drawing this asymptote and this asymptote, pulling it down, and go away. Okay. And I get a cutoff frequency of 350 kilohertz. I get my omega naught. I find the gain at that, which was -5, right? Which then turns into 0.56, and I get a damping coefficient of 0.89. Now, how is that Bode plot generated? I just swept the phase. You can see every dot is a sine wave that I input and automatically measured and averaged it and sampled out the noise. And so the magnitude is what was the ratio of the peak, and the phase was take the delay and scale it by the period and convert to phase angle. Okay. Or it just might, no, actually it just says measure phase. Okay. And you read that. So then I made an RLC circuit, and I knew I knew the parts that I had used, but again, the parts aren't the same. You know, there's a variance in the R, L, and C values. So I changed the R, L, and C's to get what I measured, right? So you can see that it's pretty well overlapped. Now, the trouble. Oh, well, it's not trouble yet. I run it in LTspice, and you can see this slight peaking in the step response, which, yeah, it's 0.89 is underdamped, but not very underdamped. So everything is great. Yes, I'm going to be the best teacher ever. Oh, man. So what we have here, yellow is the measured output of the function generator, and green is the output of the filter. Does yellow look like an ideal step function? So when you hook up your function generator, right? Do you think when I test the function generator first, because you never know who screwed with the cables in 97, right? It happens to us all, wherever we take 97. It's almost like done that way on purpose to get you to check your cables. Oh, no. All right. I'm getting a square wave. So, I mean, this is the input, right? Huh? Now the output looks like a low pass filter, right? So here it is on the scope. This is me like behaving like a real person, and I see that input, and it's a notch filter, right? Because I should show that. Okay, do you see? It's very hard. You see that there's blue right here, and it goes down and comes back up. If I expanded that shape, okay. But how do I know it's a notch? Well, it's passing the edge, right? That's the high. And it's passing the DC, that's the low pass. And it's not passing in the middle, that makes it a notch. All right. So when I hook it up to, it's by itself, it's fine. The Bode plot is fine. It's all the same circuit. What happened? Well, function generators have a 50 ohm impedance on the output, right? And so this could have been avoided by choosing values that were much, much greater than that. But I didn't have them in my office that day. All right. So now when I put in the 50 ohms, right, and then I measured this would be the output, there you go. You're getting the notch filter just like you see. Because this part is coming from the function generator. Now why is it a notch? Well, what you do is you just do voltage division, right? I have the output of the whole circuit. I mean, what's the impedance of the whole thing? And then what's the voltage division here? You just sum it and you get a notch filter. That if you set RS equal to 0 or everything else big, it goes away. Then the other mystery is why did the Bode plot work? Okay, and I'll describe how you put in a sine wave and you measure the ratio of the input and the output to get the magnitude. So why was that working and this wasn't? Ratio of the input to the output. Well, yeah. Huh?
Like input gets affected by
Which one? Where's notch? No. You're very close. So some are saying it's affected equally. Well, it is, but what's going on is it's the ratio. So if we look at the Bode plot, and let's take the blue line, and let's take 10, 90 hertz, 90 kilohertz. We'll do the red. Oh, it's down by the input, it's the ratio of the input to the output. So even though the input is down 30 dB from where it should be, it's just the ratio of the two, right? Where the step response is just measuring it raw. It's not comparing it to anything else. So you guys are all on the right track. Good job. Anyway, so that is a case study on how being able to identify what's going on an oscilloscope can help figure out what's going on. And it's certainly real, right? But notice, what I needed was more theory, right? And I'm not accusing you from writing that on Reddit, that you want to leave school so you don't have to, okay? I thought a lot of the same, all right? And what I found is that in a real system, let's just say there's a lot of distracting things, even noise, and that sometimes the simple theory is what is the way forward for figuring things out. Many times, it's almost like a meme, instead of the cat saying something, it would be an EE student saying, "It's all 98." Maybe it's not a meme, but I've heard it quite a bit. Okay. So, yeah. Okay, so before we start the next bit, it's a little more, I think it's an easier way to intuitively go from transient to Bode and back, right? That's what I'm about to show you. But are there any questions? Yes, sir.
So, what is the benefit of using a twin notch filter versus like just a regular symbol to get rid of it?
Just hold on a second. Let me. Okay. So, to me, and I'm just going to draw it asymptotically, right? 1 millihertz, 100 megahertz, okay? And, 1K. All right. Notice all the frequencies are positive, right? And so this is getting rid of one particular frequency. Now, what you seem to be describing is something like this, where you have two notches, right? Now, yeah, I could put that at 50 hertz, and I could put that at 60 hertz, and the one notch would get rid of like the power supply signal in Europe, where they're at 50 hertz, and the United States, which is at 60. Now, if you're reading the book, we haven't really gotten into the Bode plot. Again, it's all on the positive axis. We have magnitude and phase, but really a notch filter has positive and negative frequency. All right. So this would be notch, right? And it's just, I don't use it as much. It's important in modulation, okay? And then the low pass would look like this. Here's the normal low pass, and then here's the negative side of it. So if you're reading through the book and you see something like that, and the frequency is negative, it really is just a single notch. Okay? Yeah, that's a good question. However, no. But on a graphics equalizer, you could have these filters where you're multiplying the frequency range, making it bigger, and attenuating it. So it's kind of like a band notch. Or maybe it's a band filter, band pass, but you control the gain of it. So um, that's a whole other ball of fish. Did that answer your question?
Yeah.
Okay, good question. Now, which one did you mean? Did you mean the one with the frequency? Or did you mean our actual? When you asked the question, were you thinking of this? Okay. Yeah, all right, yeah, great question. Yeah. Okay. All right, any other questions? Okay. So let me adjust myself a little bit. So if you have a transfer function, right, and you multiply it by the input. So this is, this is the transfer, and this is the input, and then you multiply it by S, okay? The limit as S goes to infinity, so if the function of time is the inverse Laplace transform of this, right? That gives you the function at time equals 0. All right. Same deal as S goes to 0, F it's the same F, right? Is here goes to infinity. All right. So let's call that frequency. And we'll call that time. H S Okay. So if you have a Bode plot, you have a function times whatever input times s, and let s go to infinity, that's out here, right? That gives you what's happening at the beginning. And if you let s go to 0, that's what happens when we let time go to infinity. Now, what is infinity, right? Well, for a first order system, 5 tau, anything greater than 5 tau is like close to infinity. All right. A little bit, that's like the algorithm, right? So let's just say h of s equals omega naught s plus omega naught. Xs equals 1 over s, right? Step, right? So let's just call it f of s equals omega naught s plus omega naught times the step times s to make the algorithm work, right? And now we get omega naught s plus omega naught. Great. Huh? Yeah. And now, okay, that's a good question. It seems a little bit redundant, right? Because the s cancels. But if you want to know the ramp, well, this would be 1 over s squared, right? And then you would only cancel one s. So it's, bless you, it's good for anything. But what I like it is you kind of get back the original function, right? And let's say s goes to infinity, right? This gets much, much bigger, and it swamps out that term and drives that term to 0. Okay. S goes to 0, we get omega naught divided by omega naught, and it goes to 1. So over here we have S goes to infinity, goes to 0. F of S at infinity is 0. F of S at 0 is 1, right? And now F of t right? So when s goes to infinity, that's like f of t at f of t at 0. S at infinity makes t 0. S at 0 makes t infinity. So f of t, and let's make sure I get it right, So at infinity, f of s goes to 0. Infinity means t is 0. F of t is at 0. And this is the opposite. So really, when we look at time, right, we have this point and we have that point. And the thing is, and it's the same because it, you know, it's just greater than 5 tau. Now, yeah, you would know that it's going to do that. But you can just tell from those two data points that it's a low pass filter, right? Because it's rounding the edge, blocking the edge, and passing the DC. Okay. Second order, high pass. F of S times the step times the S just equals the original H of S. Right? So f of t equals the inverse Laplace of H of S, right? And so f at t equals 0 and f at t equals, a large number equals f. S equals to infinity equals f. S equals to 0. Well, when s is 0, right, that's 0, that's 0, and then you have 0 squared divided by a finite number, it's 0. So s at 0 is 0. At high frequencies, the s squared term dominates everything else, and we get s squared divided by s squared, so it's 1. Right? So in this case, we start off at 1, and at some point, we're 0. Okay? So here we start off here, and then we end up here, all right? And again, it could be overdamped, critical, under. That part doesn't matter, right? But you can see that it starts high and ends low, passing high, blocking low. You can tell it's high pass, right? Just from there.
it jumps up to 1 and then it goes to.
Here, let me draw a little better. So, there's no step, there's no output, or it's 0. Then at the edge, the high pass filter detects that edge and passes it all the way through, and then it decays somehow back. Okay? So yeah, the question is this, it starts at 1, well, it does jump with infinite slope. We know it's not infinite, but it looks pretty close to infinite on the oscilloscope unless you zoom in. Okay. All right. Okay. That's the numerator, and it's a bandpass. Now, again, the denominator is the same. Okay. So, again, f of s equals h of s. For the step, mind you, this is just for the step. But that's why I like it as a test vector. Okay. So f of s equals 0, f of s equals infinity. Okay, f of s as at 0. Well, this is 0, 0, 0. Even though it's not squared, 0 divided by a finite number is 0. Okay. Infinity. Well, the s squared term is dominating these here, so they fall out. Then you have s divided by s squared, which gives you 1 over s, and it goes to 0 in both spots. Oh, yeah. Oh, yeah. Whoops. So that means equals f t at infinity is 0, f t at 0 is 0, and we're kind of left with this. You start at 0, and you end at 0. So you think nothing's going to happen. But of course, something does happen. And this is not part of the theory. It's more of a hack or an intuitive way of thinking about it. What if you're at the middle frequency range? You're not 0. S isn't 0. It's not infinity. It's somewhere in between. Well, this would drop out. This would be bigger than that. And then the S's would cancel out and you'd be 1. Okay? So you might think that, it's going to go up and it should be bandpass, right? So I'm going to come back to that. The denominator's the same no matter what, right? in this example. The notch has both, right? From previous things, for the step, f of s equals h of s, f s equals to 0. Okay, so if s is 0, right, this goes to 0, right? It's probably better if I write it out. So if s goes to 0, this drops out, that goes to 0, and that's 0. You get omega naught over omega naught squared, and so it goes to 1. F s equals infinity. Well, now s is driving it. S squared dominates these terms. S squared dominates omega naught squared. So you're left at high frequencies, s squared divided by s squared, which is 1. So it's 1 both ways. Okay. So that equals to f t equals infinity equals f t equals 0. And now we are left with this. We start at 1, and we end at 1. And yeah, that same kind of intuitive thing. In the middle frequency range, this part drops out, and this part drops out, and then you have 0, because it's not there, divided by non-zero, and so it goes down, and you get the notch look. Okay. Let's see. So okay, so just to summarize, for low pass, at high frequencies, we're going to 0. It passes low frequencies, so it's 1. The high pass is opposite. Easy peasy. The band pass, remember, right? Think about, no, the band pass is doing this, right? It's blocks low, blocks high, passes middle, right? And then the notch passes low, passes high. So then f t equals 0 is fs at infinity. So I just should copy down that column. And then ft equals to infinity. I should copy down 1, 0, 0, 1. X more. No. All right. Wrong class. Okay. But, I mean, there you have a very formal way of looking at it. I'm just going to do the but you know, when we look at that transfer function and we go for low frequencies, I set s equal to 0. I go for high frequencies, I set S equal to infinity. And that's where it creeps in, where we kind of say S is actually F, right? It's not really. S can be real plus the imaginary. And when S equals, when we do this, that's Fourier analysis, right? Everything's a sine wave, and the sine waves have existed forever, right? If you have a step function, it doesn't exist forever. It has a beginning, middle, and end. Well, no, it doesn't end. It stays high. So then we have S equals real plus the imaginary, right?
Is there a better way to find out what happens in the mix than just sort of kind of like taking the limit of
I
half?
mean, besides LTspice or. So is there a better way for the middle? Well, no, because it would cancel out. Or you want to know, like, is it over, under, or critical? Well, at that point, you just would know what that looks like, okay? And we're really, I'm just saying so if I want you to pay attention, but I'm not gonna, this isn't gonna be a midterm question. The final exam question is that you were testing the transient response of filters. You had 4 oscilloscopes on an RLC, and you're doing the high band, low, and notch filter all at the same time. And you see the beginning of the step function, and you see the end. But somebody pulled the fire alarm in between, and it upset everything, and you're missing the middle part. What is what? What is high? What is low pass? What is band pass? And what is notch? So what's A? Low, right? Now, of course, anything could happen, right? It could be under critically damped, but it goes, you know, it's blocking DC, passing AC. What's B? Band, right? It's blocking low and high. What is C? Yeah, it's, wait. Oh, it's 10, oh, yeah. Whoop. It's passing the edge and blocking DC. And then D is the notch. Now, I know we get tired. If you put notch for everything or low for everything, I'll at least get a quarter of the points. Please don't do that, because that means you're guessing, right? Well, the evidence strongly suggests you're guessing, right? I don't know what's going on. Okay. Are there any questions? All right, any questions on anything? Just, well, no, Naomi raised her hand first. You were just too hesitant. Like the official plot one, like the notes. Right, but I mean, the ones that I actually used LTspice or something to do, right? Yeah. Notes on using the pitfall. Well, actually, it's shows up in more than one place. Okay. Oh, but you want the transient, right? That's actually the pitfalls. So let's not do the pitfall one. Okay. And then which filter? All right, bandpass. Okay. Now, look at red. Does it not look like a high pass, right? And on the time scale in question, it almost is, because it's underdamped and one pole is so far away from the other and the slow pole is dominating. Like the pole that allows it to rise is so fast that it rises right away. And the pole kind of in charge of decay is very slow. If you zoomed in, you would just see a slight ramp. The blue is, you can see there's a little, maybe, I mean, okay. So see the blue, you can see it start to come up. And then the band, yeah, it's oscillating. You can see it come up and then it decays. The underdamped. But if I were to zoom in on that, you would see that it's not a straight step response of a high pass. That being said, you know, on an oscilloscope and function generator, you don't have an infinite slope anyway. And so I would probably switch on the nice little ADLM 2000 and use the Bode plot function. Because remember, right, you start off at low frequencies and high frequencies. And so the low frequency breakpoints and the high frequency breakpoints can be seen on a logarithmic axis. So in time, it's not logarithmic. Maybe if I set it to logarithmic and took out 0, right, you could see it better. Yeah, maybe that's a better way. But even in a regular high pass, it's not going to have infinite slope. But that's a great question. All right, Joe, are you ready for your question? You were just joking. Okay. All right, anybody else? Anything at all? We have advising questions, courses to take, exams. Well, I just found out that there was 2 sections and now there's 1. I mean, it takes days. I mean, I wasn't told about it, right? But, and I don't know why it got canceled. That's a bit weird. It's like time or something. I don't know, but it was full. Huh? You still having trouble with your allergy meds? I'm sorry. Thanks for coming in. Yeah. Well, the thing about 7:30 a.m. is there's plenty of parking, and the pollen levels are low early in the morning. So I hear you. Okay. But a lot of part-time faculty have full-time jobs, and so you really, they do make excellent instructors because they are using the theory, right? And yes, sir. 10. So go look. So I have every relevant 110 final posted, most with solutions, right? And that's what you should expect. Although the last question can vary, right? And so the question is how many questions on the exam? 10. I do have a document with question 1, sample problems, right? 2, different kinds of problems. So for the gain bandwidth, right now on the midterm, it was find the maximum frequency mathematically, but you might have to do it graphically, right? Or sometimes there's this isn't working, why? Well, let me tell you, in general, it's gain bandwidth. Although you could have the power wrong, but I make it that there's only one mistake. But so there's 3 problems from exam 1, 4 problems from midterm 2, and then 3. And usually we have controls, we have system ID from a Bode, and then free choice. All right. Free choice, my free choice. I'm not telling you. But you can see the pattern. You'll see the pattern. But it's usually some kind of Fourier interpretation, right? You have 4 signals, 4 Fourier spectrum, which is which, right? The other ones are, here's 4 waveforms, what can you make into a DC power supply and how and why and all of that, right? Yeah, you can just think of it as like a screening interview question, like that one, okay? So yeah, by going over the Bode plot, like what does the Bode plot mean? That is actually also reviewing the Bode plot for the final exam. So on Monday, yeah, I have a lot of exams online. We can't get through an exam in one time. So I really want you guys to come in with what you don't know, right? And ask questions. So you guys are really going to drive Monday, okay?
There's lectures next week too.
Yeah, right. Last I checked, we have Monday, right? The last day of class seems to always be on a Monday. right, that there's the dead day, right? We're on. Yeah,
Okay, so
so we review for the final. Modulation is an application of Fourier. I might talk about it a little bit, but I no longer, it was always the last topic, and they cut the number of days in the semester. So I could never have an exam problem on it, so I kind of drop it. If you want to know about modulation, well, 160 when it becomes available. Or read the notes that exist from before and go from there. Okay? All right, everybody, have a good day.